All right, my outstanding friends. Once again, we meet in the pursuit of the interest of learning about things and the truth about things. And they have been looking into this volcanic eruptions creating ice in the sky. Well, that's interesting. They're cloud stuff. Well, the reason is it's getting up high enough to freeze, obviously, in these tiny little particulates. It's not particularly unusual to expect that would happen. However, we do have a situation where the hail is getting very, very big and very dense and increased 300% since 1990, and it's just getting bigger and bigger and bigger every year. And we're getting more and more and more turmoil in the atmosphere. And I mean turmoil. I'm talking hurricanes, tornadoes, weather patterns shifting, melting glaciers, decomposing things under the ground, creating earthquakes and volcanism and everything. It's nothing more than spontaneous combustion, basically. You keep something capped long enough, if it's cold, it's okay. But as soon as it starts to warm up, pow! And that's what's happening all over where they have volcanism, because it's biology that's capped off. And it was stable when the earth was cold. It's not cold anymore. So we're going to be talking about this, but the real thing we're going to be talking about is the atmosphere is being crushed because of the expansion, which means compression. Compression means condensation. Condensation means moisture turns into water. Vapor turns into water. I have a compressor, a big tank compressor, and it runs and it blows your eardrums out like that. And after so many times, you have to, there's a little petcock thing underneath, you open it up and the water comes out, because you continue to crush the oxygens and the hydrogens together, and they turn into water. It's just the nature of it. So what does that mean in a world where we have extreme compression of the atmosphere, updrafts into the cold region? You'll get gigantic pieces of ice. Now, originally, we didn't have this kind of extreme weather, so they didn't push that far up. And secondly, that layer of cold is coming down. It's never going to hit us. But the layer of cold is being crushed towards the earth because of the expansion of the gases. So when this sweeps up in there, it's going to stay up there longer. And they had now, I think there was one 5-inch hail. It kill you. It was killing animals and all kinds of things, destroyed communities. And it's serious because it's not understood. As the gases expand, we got problems, and there may be a solution to this using the dipole electron flood theory, Venturi. It seems to separate the white from the black, which is nothing more than creating electricity, and it does it on the cheap. I've shown it many times. Anyway, I'm going to show you why I'm expecting this to get much worse, because of the amount of burning that's happening and these wildfires. Everything that combusts turns something that's solid and small into something that's gigantic and puffy. And that's the gases in the atmosphere. And that pushes out towards the ionization that's coming towards us from the sun. All luminous sources are pushing into us. We're scrubbing through those. As we get bigger and bigger, we scrub harder and harder. It's not a hard thing to understand. Okay, my friends, this is about as bad as it gets. It's just getting worse and worse. The mesosphere right here is 100 and something degrees below zero, and it's moving down towards the Earth. You say, oh, that's good. It's going to get colder down here. Then no, it's not good. Because on the other side of the cold is the hot. And the colder it gets and the more crush, the hotter it will get below. And the hotter it is getting up here. You have a hot zone, which is about 2,000 to even up to 4,000 degrees above zero, right out here, before you hit space. See, why would that be so hot? It's scrubbing through space. They don't even know, but this is only the white. They're showing it. It's the ionosphere. Ions are just the white particles. They are the electron, basically. And we would always consider the electron. The dark particles are in here. This is where the cold is. These are the dipoles. The hot, the hot, then the cold, then the hot again, and then the Earth is supposed to take that in and recycle it somehow. I don't know what, but it apparently was working, because the things that are cold that are in the Earth are not decaying and rotting. Well, now they are. And in addition to that, everything on Earth is burning, basically. The forests, we're burning things, just staggering amounts of gaseous emissions, which crushes us harder and harder into this scrub zone. And when I say the scrub zone, here's what the scrub zone looks like. Hold on. Don't forget, we got the Earth, and then it gets hot, and it's getting hotter here on the surface. Then it gets extremely, extremely cold. 100 and something below zero, right above the hot where we live. And there's an abrupt transition there. And then another abrupt transition between the cold and the hot again. And then an abrupt transition between where we scrub through the less dense. There's very little density out there to scrub through. And we have our gases held to our atmosphere, as I will show you all of this stuff in extreme detail now. Okay, this, I don't know where this came from, but it's not far from wrong. There's our Earth. We have a layer of atmosphere that travels with our Earth and spins with the Earth as the Earth spins. The sun has the same thing. They have a layer of atmosphere that surrounds the sun that primarily moves with the sun, but the sun radiates out and it does not come back. Their particles don't come back. We have a magnetic field that pulls our particles back into the poles. The sun squirts and they don't come back. However, when they have to breach this zone here, it gets millions and millions of degrees because it's pushing through into the particles it's scrubbing through and creating extremely millions of degrees. Only 10,000 on the surface. They have no explanation for that. It's 10,000 on the surface, a million here. They have no explanations for ours. It's 100, and so let's go with that on the surface. Out here, it's thousands. Thousands. And then just below the thousands, it goes to minus 100. Look, thousands out there, millions out here. No explanation whatsoever for this. And again, here's the temperature zone for us. Thousands of degrees out here. This is Celsius, but in Fahrenheit, thousands. And there's an abrupt transition between the dipole. Hot, cold, 100 below. Everything's a dipole. Then this is cold, so that part of the dipole has to have the hot side, and we're on the hot side. So the hotter it gets here, the colder it gets here. The colder it gets here, the hotter it gets here. The hotter it gets here, the Earth is supposed to absorb it. It can't absorb it anymore. It's just, that's why everything's melting. The glaciers, everything. So that's our problem. Now, if we continue to expand the envelope of our gases, it's all over. I think it's in trouble now, but you can do only what you can do. And why is it in trouble? Here's the layer of gases. You see that? The Earth is spinning. Now, this is California right here. And this is the flow of gases. Now, this would be on the East Coast, and I think there was an extreme, or somewhere on the East Coast area, extreme storm here. because you see how dense that atmosphere is right there. That's serious. But they do have this both in these zones. Now, is that normal? You see how less dense this is down here than that spot and that spot? Is it because of the spin that's impacting here, coming into the sunlight? And because they do have spots, and I'll show you on the sun, it has the same thing. But we have a field that brings our particles back in. The sun does not have that. The sun squirts them, they never come back. Well, some of them do. You see back here, they come back a little bit. But here, they just trail off, they just spit out, spit out, spit out, spit out. And that's what we have to work our way through. The sun creates the particles of light just by scrubbing through the universe on the arm of the galaxy and dragging all the planets behind it. So we have to go through that solar wind because of all of that. There's a lot of particles that come off here too. It's not just sunlight. That stuff spits all kinds of stuff out of there. Chunks of stuff as well as particles of sunlight. Mostly in the very small bits because they got to break through that barrier outside there, and it just tears them to shreds through that last layer coming out through here. So I would expect, you see OH minus OH, it's a lot of ionized stuff. Ionized means there's a lot of extra electrons just floating around. Now, are these the gases that they're talking about? I don't know. Nobody knows what happens here at that zone. I would say it's going to tear molecules to shreds, just shred them. And you'll end up with the tiniest bits, which is basically light, muons, electron neutrinos, and some little chunks here and there that aren't big, like, bombs in the atomic range. All right, this is a little picture I drew that hopefully will make it a little more obvious, easy to see. Now, the sun has the same thing we have. We have this circling us. They have the same thing. Out at the corona, they spit out. Now, you see this? This is a little spring here. That's a fast spinner. That's in the blue range. Then you have a slower one that's come down here into the red. It's a spectrum: red, yellow, green. And then you get into your ultraviolets and stuff. Anyway, that's where it hits our surface here. Now, the moon re-radiates primarily. I don't see, the moon might have something going on there. I don't know. We saw some stuff in space that just mind-boggling. But primarily, it gets hit by the sun and re-radiates. That's why you only see moonlight in that lower spectrum, because it's just bouncing light back off it. It's not spitting it out like it is out of the sun. That's why we get all the different colors from the sun all the way up into the ultraviolet and the whole 9 yards. Okay, so here's what I'm saying. This is a disaster. As this gets hotter, it's pushing down harder against the mesosphere. The mesosphere, because this is getting hotter, this has to get colder. This is their dipoles. That gets hotter, that's getting colder, and it is. This gets pushier, this gets pushed down, and it is going down. Yes, it is. As it goes down, it gets colder, first of all. Secondly, the compression down here pushes more air up into it, and the hail that's created in this hundreds of degrees below zero, or way over 100 degrees below zero, the more moisture you push up in it, the bigger the hail is going to get. And right now they're talking it's increased radically, and it's getting much more hail. I'm watching the weather, and it's just not good. And I know there are areas that are not good, and there are areas where you have rise. And it's because a lot of it's due to elevation and some other things. But this is not good. The higher we compress the air, the more these things are going to affect us. And Well, let me just see if they agree with what I'm saying in chat. Let's find out. All right, I asked about the size of hailstones. Studies observe significant increase in both size and frequency of large hailstones worldwide. 300% since 1990, 14 centimeters in diameter, 12.7 centimeters in diameter. Australia, one of them was 14 centimeters in diameter, and they're getting bigger and bigger every year, just continuously. So what about the mesosphere? All right, don't forget the mesosphere is that cold layer. Above that is the extremely hot layer, and then you go into outer space, which we're scrubbing through. So the hot layer is getting hotter and hotter and pushing down more and more. So it pushes the mesosphere lower. I says, is the mesosphere getting lower? Yes, the mesosphere is getting lower. The change is largely due to human-caused climate change. It's due to expansion of the gases. Yes, absolutely, I agree. They said, I'm not too far off from what they're saying, but it's not carbon. It has nothing to do, well, it does have to do with the carbon. It's any gaseous expansion. Any expansion creates more pressure, condensation, pressure, and that creates more and more hail, and the hail will get to be the size of basketballs. I'm going to tell you right now, I don't see any other way, any other possible size. They're about this big, not a softball size, they say. What if they came down this big? I'm serious. This could be very, very, very serious. And I think we have to start to think about this in a whole new way. Just you gotta think, even though it's scary, you gotta consider. That's all I'm saying, just consider. You see this? This is not nothing. The cooling has led to a drop in the altitude of the mesopause. That's the layer at the mesosphere. It's pushing it down roughly 150 to 500 meters per decade in some regions. So the mesopause separates the cold layer from the warm layer that we live in. And it's being pushed into our layer. People say, oh, that's good. No, it isn't. It's crushing the layer below, and the water right now, the moisture that goes up into there, is creating a lot more frequent hailstones and bigger, and the crusher it gets, the colder it gets, and it's doing both of those things right now. It gets down here and it gets pushed up in there. It's going to be very, very serious. Don't forget, the mesosphere is getting colder. So as this warm air comes up, it's coming down and getting colder at the same time. And that goes up, more and more hail, gigantic stuff should be coming down. And I'm telling you, and it won't be long. All right, so if you've been paying attention at all, you know we got a serious issue. We got to get rid of some of that heat. How are we going to do that? How are we going to get rid of that heat? I think there might be a way using the Venturi technology that we discovered. And you have to squirt this out far enough away that it won't come back. This is just nothing more than heat. They don't realize it. They put a tether up in here, and the tether was about as big around as, let's say, my finger. When they looked at it, it was a mile around because it got surrounded by all this, and then it exploded because there's just too much attraction by that white. But if you could drag that into space, drag that white out of there, that's nothing more than just like discharging a battery. This is nothing more than charged up a battery. Nothing more than like you had just too much juice in that battery and it wanted to explode. And if you could squirt it out, could we squirt it out? Maybe. How would we squirt it and where would we squirt it? We might be able to do it right here. Something like this. Now, how would we do it? I'm not sure. But if there would be some space laser or something that would shoot and push through a Venturi out there and pull all these particles out from this layer. Here's what we need. Here's how it would work. You know what? Let me draw this out. Because what we need to do is take the particles out of here, which are the moisture. All right, H2Os and so forth. Now, how we do that, I'm not sure. But shoot it out through here with a laser cannon that would do the Venturi effect and just splash it out far enough away it wouldn't come back. And when I say the Venturi effect, what am I talking about? This right here. We'd have to have that out at the edge of space and pull the particles that have mass, because you have to have mass to pull those particles out. So that something's going to have to be there that is squirted through that layer, and then the white particles will follow it, just like this. You squirt it through the layer, and the white particles will, there's so many of them, they want desperately to be attached to anything that has mass. So we put this thing right here, the Venturi, somewhere here, shoot it through there, and out far enough that it gets away from the Earth, and it would, like deflating a tire. This may be possible. I can't get anybody to pay attention to anything I show. And we found the same particles they found at Fermilab. These are the two particles. There they are right there. And this is the one we got to get out of our atmosphere. The black one is dark matter. That's mass. This has no mass whatsoever. And that's what they say. Everybody knows that now. It has no mass. But it has a huge field. This is what you put in your battery when you charge it up. When you charge up a car, the car weighs 4,000 pounds. There's no electricity in it. You can't drive it. Fill it up with electricity. Still weighs 4,000 pounds. How did that happen? All you put in was the white. All you put in was the glowy part. It has no weight to it. And I'm talking, the car might gain some weight, but it would be like nanograms. That's like billionths of a gram. They can't detect it. Let me put it that way. So, we know that doesn't have any weight. And that's what they say, that this area is a vacuum out there because there's no mass. It's nothing but particles. It's nothing but those white particles out here. They say it's a virtual vacuum. No, it isn't. It's a virtual hotspot of white only. And then you get down here to the other side of the dipole, which is the dark matter side, that has mass. It's the mass side. Let's go with that. This is the non-mass side, the energy side. This is the mass side. I call them dipoles. You call them whatever you want. But if we can squirt that stuff back into space, I'm telling you, that may work. And the only thing I can see that could do it would be the Venturi, this right here. And it might be just like we're using a low-cost laser and squirting it out. And how much you could squirt, I don't know. How many lasers could you put up? I don't know. Where would you put them? Well, I don't know. But I would think these are the areas up in here where you have the most interaction with the external area. This looks a little too hot. But if you pull it out of here, it doesn't matter. It's going to deflate up through. It doesn't matter where you pull it out of. It's going to be okay. Well, I mean, it's going to pull it from somewhere else. In other words, if you don't have to shoot it out of here, you can shoot it out of here, and that's just going to sink just like a balloon. And the balloon goes down. Because we got nothing more than one big balloon surrounding the Earth. And it's the ionosphere. I really, really, really think somebody should talk to me about this. They just are missing a boat on everything here. And we're just headed down the road for destruction. I'm telling you right now, burn, baby, burn. I don't think that's a good idea. We could use this, I think, to create free energy. That is just solid energy. That's exactly what you create when you do a generator. But a generator takes a lot of work to rip that white away from the black. We didn't have to do anything at all other than force the particles to come into what's called a Venturi, which is so tight only the white could squirt through, because the black is a fixed particle. The white is not. And here it is accelerating. You're not supposed to be able to accelerate light. And there's the particle, and then it explodes here, and it's so much reverse electromotive force that all of the other fields that are here in space that you don't even see, you would never know that they're here, and they're lighting up now brilliant because they're getting pushed back at. They think they just hit a wall. All of them. This is a subatomic nuclear explosion. That's exactly what it is. And this is the interference patterns. They're not interference patterns. Those are repulsion patterns. The white hate each other. That's why they turn into a shower. Get away, you get away, you get away, you get away. And then they just set up these lines. And light spins just like this. The particle spins straight through. And they're all three are the same particles. They're exactly the same. But the green spins much faster than the red. This is the red, and it's actually spinning here. You don't see it, but it is spinning. I have all that stuff. I have so much information on this. I have hundreds and hundreds of pictures. And, by the way, this is Fermi Labs right here. See that? The glowy edge around the black particle. There it is. There's the black particle with the glowy edge around it. This is taken right off of Fermi Labs' website. And then this is the other particle. These are the two smallest particles they can find. And they are. That's the muon, which is this one here. And it's also dark matter. And these two are the electron neutrino, which is this one. And it's the energy. And we accelerated that. Same particle. Accelerated it right out of its own wave. Until it hit the Venturi here. And split. The black disassociated. Call that whatever you want. I call it disassociation. You could call it fission. So when something goes away from something else, it's fission. They fizzed. What came through here? Nothing but the electron showers. What did the black balls do? They turned into sterile muons. This is what they see in Cherenkov radiation. It's exactly what we see at the Venturi. And electron showers, if you can harvest that right there, which we can, we could put a harvester right there. I don't know if you'd ever be able to use the amount of energy you could create doing this. It would be virtually unlimited. All right, this is from CERN. They do protons. They got to be huge things. They got decay into hadrons and flux of this and that. They wanted to get down to the energy of neutrinos, which is a few 100 billion electron volts to a few trillion electron volts. And you're starting off with just hundreds or, hundreds of millions, let's say. Certainly not hundreds of billions. So the increase in energy is staggering. And I'll show you their graph, not mine. The graph, I believe, is CERN. Okay, this is the laser coming in. And it's only got this much energy. Very low. The little u means energy. Hold on. All right. So it's only got almost no energy. And as it comes in, it starts to build energy. A little more, a little more, a little more. Because it's starting to push and create energy. Whenever you push something against something else, you got energy. You push something against nothing, you don't have any energy. So it's starting to build energy. And then all of a sudden it hits the Venturi. And the energy goes through the roof. That's energy. It's building energy, a little bit, a lot, right up through the roof. What happens with the electrons? This is the number of electrons in the shower. As it comes through, it's like the beginning here is here. It's just starting, and you're getting some electrons, you're lighting things up a little bit, and it's starting to sense a reverse in this area. The pushback, and as it comes forward a little more, it hits the Venturi, it drops down to nothing, and once it comes through the Venturi, right through the roof. The number of electrons, exactly what we saw, exactly. So the energy here should be staggering, and you should be able to carry that around in a little lunchbox with a floating ground, no connection to the grid. Okay, I love this Venturi. you can see we accelerated light. There is just no doubt whatsoever about it. It's just not in question. And a Venturi is known to do that. And it's separated and created exactly what they claim was the muons and the electron neutrino, the showers. This is not me. I didn't do this. Muon neutrino creates the black muon, sterile, all by itself. The electron neutrino, which was attached, goes into the electron shower mode. There's the black ones. And then the black ones jump right back in. And that's because we created this fission and fusion. That's all it is. It is what it is, and that's what it is. There's no denying it. Unless you want to deny it, we can talk. Now, this is my thoughts on how we could get free energy. You take a little thing, this is just a Geiger counter, but it's a little mock-up thing. You could have any kind of outlet you want in this, any kind of voltage, USB, ABC, DE, all that, anything you want. Now, what do you got? A laser here, which is what we use. Well, hold on, I'll show you what we did use. Because it was not what you call a big deal. That's it right there. That's what we used on the cell phone. The CMOS in the cell phone. This is from 2012. Galaxy S3. So we were doing these experiments and getting the same results as Fermilab and CERN and everybody else. However, they wanted this to be huge, huge, huge particles. We were starting with light, so we didn't have to dig through all the debris. And light is not dangerous. If you surround this with something that's not really penetrable, basically, it comes back together so quick, I can't see how you're going to get hurt. It's going to come back together, like that far away. You put your eyeball there, well, you might have a problem. But this I see as shooting the Venturi shooting the laser through the Venturi, the black stays back, the white comes through, we put a collector right here. Just like that. And you could probably have 1,000 of these little lasers right in here and have just squirt energy out of there coming out of your ears. And you could use this kinetic and there's potential energy. Potential means you just put it in a battery to store it. I don't even know why you'd have to do that. You'd have so much potential, kinetic energy coming out of you, you just use it right in. And the laser doesn't make any noise or anything. It doesn't do anything. You just sit there, create electricity, if it works. But it's got to be looked at. And this is all we used was this little stuff right here to do this. And that's what upset them. I know, you step on people's feet, they don't like it. But I thought, in the interest of science and trying to hope to save the country, and energy, free energy, well, somebody would talk. No, it doesn't work that way. Because it wasn't just Fermilab, Don Lincoln, who I have the most trouble with, but it was all of them, every one of them. Refusal to engage. The only one that did engage was the University of Geneva, because I went there as a student, and the professors said, no, you can't use CMOS, and I said yes, and we went through the whole rigmarole where I said, we're using light, and now they did upgrade to CMOS. Eventually and if you look it up, CMOS, yes, CMOS will see muons, electrons. Now they admit it.